next topic in section 2.5 is the so-called adjoint operator. And also here we have to recall something about the spaces before we can come to the operator. So let's quickly recall how the scalar product of two vectors in Rn is computed. And of course we know how that goes. You just multiply x1 by y1, x2 by y2, and so on until you end up at the last position. But this expression can also be written as the product of two matrices, which are a 1 by n matrix and an n by 1 matrix. And this just denotes the usual matrix product. So the result will be a 1 by 1 matrix that we just interpret as this number. So all I'm saying with this computation is that we can abbreviate the Rn scalar product of two vectors x and y also as y transpose times x, where the times here denotes matrix multiplication. Okay, now let an operator A come into play, which is an operator from Rn to Rn, or we could just say it's an n by n matrix. And then let's write the same scalar product with A squeezed in front of the x. Now by the formula that we just derived, we can rewrite this as y transpose times ax, and then remark that this is actually also just matrix times vector multiplication, and recall that A transpose is A again. Okay, then in the next step you use this little rule for the transpose of a product to simplify this expression into that one. Okay, but now finally by this rule, let's label it with a star, we can rewrite this again as a scalar product, and it's the scalar product of x with A transpose y. By the way, we also used star here, right? Okay, so that's a very important insight. So the scalar product of ax and y is the same as the scalar product of x and A transpose y, or to say it differently, the job description of the transpose is just to bring A to the other side of the scalar product by putting a transpose there. Okay, now let's move from real vectors Rn to complex vectors Cn here. Let me just put this in here a little bit ugly. What would change? Well, now all my little x's and little y's are complex numbers. And we have learned that you have to change the following. You have to put complex conjugate signs on top of the little y's, which you would also have to do here and here before you multiply them. Well, this procedure of passing from your column vector y to this row vector that is also complex conjugated would now be abbreviated not just by the transpose but by what we call adjoints. So we would put a little star here instead of just a transpose sign, right? Okay, so in the complex setting our formula star also holds, but with a little star instead of the transpose sign. Now let's just carry this through for our second computation, where now A is an complex n by n matrix, or I could say is an operator from Cn into Cn. Well, all we have to change is the transpose signs become little stars, and also here there's the star, and A can be written as A star and then star again. Okay, and also that formula exists with a star instead of a transpose sign. So you would just carry the star through wherever your transpose sign used to be. And then with the new star equation here, you end up at a very similar result, but again with the star instead of the transpose. So we could take this highlighted in blue equation as the job description for the adjoint matrix A star. Of course, well, for finite matrices it's a lot easier to just describe A star by the complex conjugate of the transpose. But in our operator world, matrices are not always at hand, so we need this other description for the adjoint operator. And that's going to be this equation that we highlighted in blue. So let's attempt a definition. So let us start from an operator A, from x into y, and we will see in a minute what features our spaces x and y need to have. Okay, and now here comes the definition of the adjoint. The operator A star from, well, we will see to, well, we will see with, and now we copy exactly the blue equation. So ax comma y shall be equal to x comma a star y, and this shall be true for all little x's and all little y, is called the adjoint operator of A. Okay, so we clearly have some gaps here that need to be filled. Maybe let's start over here. We are applying A to this little x, but A is taking elements from capital X, so little x must be in capital X. Okay, and then this result of AX will be in capital Y. And then it is placed in a scalar product with little y. Well, this is telling us two things. First of all, this little y has to come also from capital Y. And the scalar product here has to be the scalar product in Y. Let's just make this clear by writing our capital Y as a subscript here. Okay, now let's come to the other side. Here, little x, from which we know it's in capital X, meets another vector, so that clearly this second vector here has to be from capital X also, and this scalar product has to be between vectors of x, so it must be the scalar product in x. Okay, now finally, after all these clever thoughts, we can fill the gaps here and here by checking to what is A star applied. Well, A star is applied to little y, which is coming from capital Y. And if you do that, you get an element from x, so A star must map into x. Okay, now that's your definition of the adjoint operator. Okay, to be honest, we are not quite finished because we saw it before that every time we say the operator or element or something, one has to show that there can be only one, so the uniqueness of this operator has to be shown. So one has to show that there is only one operator that can do this job. But well, let's this problem not be our business here. And let's not forget the other gap that we left in this definition. So the spaces x and y both have to have a scalar product, so they both have to be Euclidean spaces. Possibly even Hilbert spaces, but not necessarily so.